This is Project 2 for Group 12, including Austin Thompson, Demetrius Continus, Mark Blue Lane, and Hunter Johnston, where we built and analyzed and flew a glider made out of balsa wood. So here's the original glider without a tail. Its aerodynamic center is at 12.5 centimeters, and its center of gravity is at 17.1 centimeters. And here the center of gravity is actually behind the aerodynamic center, and that makes this configuration unstable. And that's because the aerodynamic center also acts as the neutral point of the glider, assuming that the fuselage contribution to the overall moment response is negligible. We had to design a horizontal tail for our glider in order to stabilize it. And in order to design the horizontal tail, we broke the aircraft down into components and analyzed their contribution to the stability of the glider. Here are the separate glider components: the main wing, the horizontal tail, the vertical tail, the fuselage, and the point mass, and they all separately contribute to the overall moment response of the glider. Here the horizontal tail is the stabilizer, the vertical tail is the provides directional stability, and the point mass is a weight that we applied to the glider in order to move its center of gravity. And here we have independent variables of our configuration in red, and that is the wingspan of the horizontal tail, the height of the vertical tail, and the position and mass of the point mass that we applied to the glider. We calculate the center of gravity of the glider, and so what this does is it takes the mass of each of the components and multiplies it by its separate center of gravity, the distance of that center of gravity away from the tip of the airplane, adds all of those together, and then divides by the total mass of the glider, and this will get you the position of the center of gravity. And this will be different depending on if the point mass is applied to the tip of the aircraft or not, and that will change the aircraft and put it in a stable or unstable configuration. This is the neutral point calculation, and some assumptions have been made. First of all, it has been assumed that the fuselage contribution to the overall moment response of the glider is negligible, so it has been taken out of the neutral point formula. And also, we have assumed that there's no downwash from the wing to the tail. And this also further simplifies the neutral point calculation, and the formula can be seen at the top of this slide here. Neutral point position is equal to the position of the aerodynamic center plus eta times VH times CL alpha T over CL alpha wing times the chord of the wing. Also, we've assumed that eta is equal to 1 because the free stream velocity at the tail is pretty much equal to the free stream velocity at the wing, and that makes eta equal to 1. And also VH is equal to the distance of the aerodynamic center of the tail times or the aerodynamic center from the tail from the aerodynamic center times the planform area of the tail over the planform area of the wing times the chord of the wing. And also, in order to find the coefficient of lift curve of the tail and the wing, we've used the Helmholtz formula, and it can be seen there. CL is equal to pi times AR over 1 plus the square root of 1 plus the aspect ratio squared over 4. Using all of this, we have found that the neutral point of the glider is at 22 centimeters away from the tip. Here you can see the glider that we built. Here, this glider, the tail has a wingspan of 30 centimeters and a chord of 7.9 centimeters. Also, it has a point mass of 15 grams located 1 centimeter away from the nose of the glider. And here the aerodynamic center is at 12.5 centimeters, the center of gravity is at 21.95 centimeters, and the neutral point is at 22 centimeters. And this is for the stable configuration with the point mass. The unstable configuration without the point mass has a different center of gravity that is behind the neutral point. Here's the moment response calculations for the stable configuration. First, we stated that CM0 is equal to 0, and that causes the CM about the CG to be equal to CM alpha times alpha. And that's because CM naught of the flat plates that we used for our wing and our tail, those are actually equal to 0. So that means the CM naught of the configuration with the wing and the tail is also equal to 0. So that means CMCG is equal to CM alpha times alpha, where CM alpha is calculated by the equation in the middle right here, and we got CM alpha to be minus 0.019, and since that is negative, that actually indicates that our glider has longitudinal stability. Here you can see the moment coefficient versus the angle of attack. It has a slope of minus 0.019. It also passes through the origin. So yeah, here's the moment response of the glider. Here's the lift calculation for the glider. It's equal to the lift curve slope of the wing plus the lift curve slope of the tail times the planform area of the tail divided by the planform area of the wing. Here you can see the lift curve slope of the wing, the tail, and the entire aircraft. Obviously, the lift curve slope of the entire aircraft is greater than the lift curve slope of the wing and the tail separately. This makes sense, that's expected. Here's the center of gravity and the neutral point for the unstable configuration. That is the configuration without the 15-gram point load applied at the nose of the glider. You can see that the center of gravity is behind the neutral point, and that indicates that this configuration is unstable. And you will be able to see the instability of the glider in the upcoming videos. It is, once it starts pitching up, you can see that it does not automatically pitch down, and that causes the glider to go out of control and actually crash. Here is the center of gravity and the neutral point for the stable configuration, and that's the configuration with the point load applied near the nose of the glider. Here you can see that the center of gravity is actually in front of the neutral point, and that causes this configuration to be stable, and you can actually see that in the upcoming videos. And because the glider is able to fly further, and you can actually see when it gets perturbed any certain way longitudinally, that it actually is able to correct itself and fly further. We learned a couple lessons creating this glider. First of all, we learned that balsa wood can break very easily, and that when you make gliders out of balsa wood, you have to be very careful in order to not put the glider in any conditions where it can break. So stability is very important if you're making a balsa wood plane, because you have to be sure that the plane isn't going to go out of control and actually crash and all crazy like and break like our. We also learned that it was easier to shift the center of gravity to make the glider stable than it was to shift the neutral point, and that's because we used a flat plate as our tail, and it is not a very effective lifting surface. If we were using different types of airfoils as our tail, we probably would have been able to actually shift that neutral point back a lot easier. But since we don't really have the skills or the expertise to build um, very fancy airfoil shapes, we instead just used a flat plate as our tail. And that did shift the neutral point back a little bit, but it was actually easier to compensate for this by shifting the center of gravity up, because it was just much easier to attach a point load at the nose in order to stabilize this aircraft. And in reality, that is probably not the best thing to do because you're just adding unnecessary weight to your aircraft. But here it was a simple solution that we pursued.